Please watch my previous two videos about ARIMA model to understand more about building this model. So in this video, I am going to build an ARIMA model. So now we have determined the values of P, D and Q. You have everything needed to fit the ARIMA model. Let's use the ARIMA implementation in Stats Models package. The model summary reveals a lot of information. The table in the middle is the coefficients table where the values under coefficient are the weights of the respective terms. Notice here the coefficients of the MA2 term is close to 0 and p-value in P greater than modulus of Z column is highly insignificant. It should ideally be less than 0.05 for the respective x to be significant. So let us build the model without the MA2 term. The model AIC has reduced, which is good. The p-value of the AR1 and MA1 terms have improved and are highly significant. That is very much less than 0.05. Let's plot the residuals to ensure there are no patterns. That is, look for constant mean and variance. The residual errors seem fine with near zero mean and uniform variance. Let's plot the actuals against the fitted values using plot underscore predict. When you set dynamic is equal to false, the in simple lagged values are used for prediction. That is, the model gets trained up until the previous values to make the next prediction. This can make the fitted forecast and actuals look artificially good. So we seem to have a decent ARIMA model, but is that the best? Can't say that at this point because we haven't actually forecasted into the future and compared the forecast with the actual performance. So the real validation you need now is the out of time cross validation. How to find the optimal ARIMA model manually using out of time cross validation. In out of time cross validation, you take a few steps back in time and forecast into the future to as many steps you took back. Then you compare the forecast against the actuals. To do out of time cross validation, you need to create the training and testing data set by splitting the time series into two contiguous parts, that is approximately 75 is to 25 ratio, or a reasonable proportion based on time frequency series. Why I am not sampling the training data randomly, you ask? That's because the order sequence of the time series should be intact in order to use it for forecasting. You can now build the ARIMA model on training dataset, forecast and plot it. See from the chart, the ARIMA 1, 1, 1 model seems to give a directionally correct forecast, and the actual observed values lie within the 95% confidence band. That seems fine, but each of the predicted forecasts is consistently below the actuals. That means by adding a small constant to our forecast, the accuracy will certainly improve. So there is definitely scope for improvement. So what I am going to do is to increase the order of differencing to 2, that is set d is equal to 2, and iteratively increase p2 up to 5 and then q up to 5 to see which model gives least AIC, and also look for a chart that gives closer actuals and forecasts. While doing this, I keep an eye on the p-value of the AR and EMA terms in the model summary. They should be as close to 0, ideally less than 0.05. The AAC has reduced it to 440 from 515. Good. The p-value of the x terms are less than 0.05, which is great. So overall, it's much better. Ideally, you should go back multiple points in time, like go back 1, 2, 3, and 4 quarters and see how your forecasts are performing at various points in the year. Here is a great practice exercise. Try to go back 27, 30, 33, 36 data points and see how the forecast performs. The forecast performance can be judged using various accuracy metrics discussed next. Now the accuracy metrics for time series forecast. The commonly used accuracy matrices to judge forecast are mean absolute percentage error, MAPE, mean error, ME, mean absolute error, MAE, mean percentage error, MPE, root mean squared error, RMSE, lag 1 autocorrection error, correlation between the actual and the forecast, min max error. Typically, if you are comparing forecast to two different series, the map correlation and minimum error can be used. Why not use the other matrices? Because only the above three are percentage errors that vary between 0 and 1. The way you can judge how good is the forecast irrespective of the scale of the series. The other error matrices are quantities that implies an RMSE of 100 for a series whose mean is in thousands is better than the RMSE of 5 for series in tens. So you can't really use them to compare the forecast of two different scaled time series. See, around 2.2 percentage map implies to model is about 97.8 percentage accurate in predicting the next 15 observations. You know how to build an ARIMA model manually. But in industrial situations, you will be given a lot of time series to be forecasted and the forecasting exercise be repeated regularly. So we need a way to automate the best model selection process. So how to do auto ARIMA forecast in Python? Like R's popular auto ARIMA function, the PMD ARIMA package provides auto underscore ARIMA with similar functionality. Auto ARIMA uses a stepwise approach to search multiple combinations of PDQ parameters and choose the best model that has the least AIZ. So next I am discussing how to interpret the residual plots in the ARIMA model. Top left, the residual errors seem to fluctuate around the mean of 0 and have a uniform variance. Top right, the density plot suggests the normal distribution with mean 0. Bottom left, all the dots should fall perfectly in line with the red line. Any significant variation should imply the distribution is skewed. Bottom right, the correlogram ACA ACF plot shows the residual errors are not autocorrelated. Any autocorrelation would imply that there is some pattern in the residual errors which are not explained in the model. So you will need to look for more excess predictors to the model. Overall, it seems to be a good fit. Let's forecast.